Now look the process of charging. Electrons are going from this positive plate to lower negative plate. Electrons are going from upper positive plate to lower negative plate. Look carefully. Electrons are going from this positive plate to this negative plate against the attraction of this positive plate. Here this positive plate attracts this electron, but it is going from positive plate to negative plate. It is going from positive plate to negative plate. Although the upper plate attracts this electron, but it is going from positive plate to negative plate. To charge up a capacitor, you have to remove electrons from the positive plate and carry them to negative plate. In doing so, you fight against the electric field, which is pulling them back towards the positive conductor and pushing them away from the negative one. To charge up a capacitor, you have to remove electrons from the positive plate and carry them to negative plate. In doing so, you fight against the electric field, which is pulling them back towards the positive conductor and pushing them away from the negative one. Suppose at some intermediate stage of charging, the charge on positive plate is Q, so that the potential difference is Q upon C. Potential difference is Q upon C. Charge is Q. Charge is Q. And here it is minus Q. And potential difference between the plates is V. We can write V as V is equal to Q upon C. Let us give the letter a small q to this capital C, capital Q. Suppose it is Q. And it is minus Q. PD is potential difference. V will be equal to Q upon C. C is the capacitance of this capacitor. The work you must do to transport the next piece of charge dq is dw is equal to v dq, which will be equal to Q upon C into dq. It is given here. This is the work done in this process. Therefore, the total work necessary then to go from Q is equal to 0 to Q is equal to capital Q is the integration of this function. The integration of this function. It will give net work done in charging the capacitor by amount of charge capital Q. W is equal to integration of dW is equal to integration of this function which is given here from limit 0 to capital Q. The integration, the result is Q square upon 2C, which will be equal to the potential energy U stored in a capacitor with charge Q. In practice, this work W is supplied by the battery. This work W is supplied by the battery. As we also know that Q is equal to CV. So if we substitute this value of Q in this equation, we get U is equal to, U is the potential energy stored in the capacitor, electrostatic potential energy stored in the capacitor. It will be equal to half CV square. Here we put Q is equal to CV. U will be equal to half CV square. Q square will be equal to C square V square, and the value of denominator is 2C. So U will be equal to half CV square, and it will also be equal to half QV, as C is equal to Q upon V. Now we will calculate the energy given by the battery. Now energy given by battery in this case will be equal to the work done by battery in transferring charge capital Q across the potential difference capital V. So by using relation V is equal to W upon Q, we can write W battery is the work done by battery, is equal to QV. From here W is equal to QV. Therefore energy given by the battery, W battery is equal to QV. But energy stored on the plates of capacitor is half QV. So we can say that energy stored in capacitor is equal to half into energy given by the battery. Half amount of energy is loosed in the form of heat, light and spark, sound, etc. Electric field energy density. Now we will calculate electric field energy density. Energy stored in a capacitor is given by U is equal to half CV square or half QV. But for a parallel plate capacitor, we have C is equal to epsilon naught A upon D. Therefore, we can write U as U is equal to epsilon naught A upon D, value of C, epsilon naught A upon D, 1 upon 2 is here, 1 upon 2, and V square, that is U is equal to epsilon naught A upon 2D into V square. If we multiply numerator and denominator by D, D is the distance between the plates and A is the area of capacitor plate, we get U will be equal to this. Here AD is the volume of capacitor, volume of space inside the capacitor plates. And we also know that V upon D is equal to capital E is the electric field. Therefore, we can write U as epsilon naught AD upon 2 into E square. This expression can also be written as U is equal to epsilon naught gamma upon 2 capital E square. Here gamma is equal to AD. It is equal to volume of capacitor. Therefore, energy density small u will be equal to capital U upon gamma, means potential energy stored per unit volume. It will be equal to half epsilon naught E square from this expression.